Respected chairpersons and faculty members, a very good morning to one and all present here. The topic for my presentation for today is comparative evaluation of maximum deformation and failure forces at the implant abutment interface with angled and straight abutments at 2 levels of bone loss and in vitro study. As we all know, dental implants have been used extensively for the replacement of one or more missing teeth with remarkable survival rates. And the amount of marginal bone loss at an implant plays a key role in the strength characteristics by offering protection to the load transfer mechanism. The aim of my study was to evaluate the maximum deformation and failure force and microgap formed at the implant abutment interface with varying levels of marginal bone loss. And the objective was to evaluate the rate of maximum deformation, to evaluate the failure forces at the implant abutment interface between angled and straight abutments with 2 levels of bone loss, and to evaluate the microgap which is formed at the implant abutment interface. We had done a sampling procedure with a stratified random sampling, and this included a total of 30 implants. The groups were divided into 3, and it was again subdivided into 2, that is group 1A, 1B, 2A, 2B, and 3A, 3B respectively. The group 1 was the implant group with a simulated bone loss of 1.5 mm. It was again subdivided into group 1A and 1B, where the 1A included the implant group with angulated abutments and 1B with the implant group with the straight abutments. This is a picture which is showing group 1A, which is angulated abutments with bone loss of 1.5 mm, and 1B with the straight abutments with 1.5 mm bone loss. Again, the group 2 was the implant group with simulated bone loss of 3 mm. It was again subdivided into 2A, where it was angulated abutments, and 2B with the straight abutments. This is a picture showing the same. And the group 3, which was a control group where no bone loss was simulated, that is again it was subdivided into group 3A and 3B, where 3A was an implant group with the angulated abutments, and group 3B was an implant group with the straight abutments. This is a picture showing the angulated abutments with no bone loss and the straight abutments with no bone loss. Coming to the methodology, 30 implants of diameter 4 mm length diameter and 13 mm length were placed in acrylic blocks of 20 mm height and 2.5 inch thickness using a custom fabricated mold. An aluminum split mold of appropriate measurements, that is 20 mm height and 2.5 inch thickness, was custom fabricated, and this could be opened and closed in a horizontal axis. A hinge was attached behind the back of the custom fabricated mold so that it could be divided into 2 equal halves for the easy removal of the acrylic blocks. And on the right side, we can see that the material, that is the autopolymerizing acrylic resin, which was used for making the molds for the study. And in this picture, from this picture, we can see that a split mold has 2 lids, which was made in aluminum with 1.5 mm and 3 mm lid thickness, so that the implants could be held exposing the threads at 1.5 mm and 3 mm, relating to the simulated bone loss of 1.5 mm and 3 mm. And the lid has a bore at the center, which is 4 mm in diameter, and it was relatively used for centering of the implants. And this lid was firmly fixed to the mold with the help of screws which were connected on either sides of the mold, which could be loosened as well as tightened. So this was how the acrylic blocks were prepared. And again, we can see in this picture that is 2 rings were fabricated, which was used to confirm the 1.5 mm and 3 mm bone loss, which was mimicked for the implants. This was a hex driver and a torque wrench which was used, and after moderate polishing, the acrylic blocks were ready for loading. And again, from this picture, we can see that a spherical cap of 20 mm diameter was made, which mimicked the prosthetic crown too. So coming to the loading, so the study was done in 2 parts. That is, the evaluation of maximum deformation and fracture was done as a 1 part, and the evaluation of microgap was done as a 2nd part. So from this picture, we can see that each loading procedure involved application of force using to the cap using a universal testing machine at 1 mm per minute from 350 Newton to 1500 Newton. So then a graph was obtained. The raw data was recorded as a force versus displacement curve, and the first turning point was taken as a maximum deformation, and the flat curve was taken as a failure. And in the 2nd part, the microgap was measured using OGP Smart Scope CNC 500. So this is a loading procedure, and it was a testing of the first group, and simultaneously all the other groups and all the other samples were tested. So this was how the microgap was measured. It was measured using an instrument called as OGP Smart Scope CNC 500. And after every load, the specimen was checked for the micro gap, and 2 linear lines were taken and 2 points were taken, and the micro gap was measured and compared. So this was how the statistical analysis was done, and these are the results of my study for the evaluation of maximum deformation. And from this data, we concluded that so then when the maximum deformation was evaluated across bone loss, it was found that there is a significant difference between group 2A and 2B. And when maximum deformation was evaluated among straight abutments, there was no significant difference was found. And on failure, it was found that the group with angulated abutments failed at an earlier rate than when compared with the straight abutment groups. So this was evaluation of the micro gap. Coming to the discussion, the present study aimed to analyze the effect of progressive bone loss on medium and long-term basis. And from the inferences of the present study, it was noticed that crestal bone loss alone may not be a factor for fracture of implant leading to failure, which is in accordance with another similar study which was conducted by Aldavi et al. And in the present study, angulated implants with 15-degree angulated abutments were used, which was in consonance with the study which was conducted by L. Sheikh et al. And angled abutments causes a fatigue failure leading to fracture of an implant due to overload flexion by flexion of the implants. Seletti discovered that straight and angled abutments did not affect bone levels around an implant, which could be correlated with the results of the present study, where a straight abutments group did not exhibit any fracture. And although the quality of osseointegration was proven, it is reported that angled abutment screws in angled abutments had a rate of failure greater than in straight abutments, which is similar to the present study. In the present study, implant groups with angulated abutments exhibited comparatively huge microgap, which have occurred due to screw fracture. Compressive forces may cause deeper settling of the abutment into the implant body of conical connections, minimizing the microgap, allowing a two-piece system to behave as a one-piece. Coming to the conclusion, so I conclude that the angulation contributed significantly for deformation and failure among the different groups, and it was found that the implant groups with straight abutments could withstand the maximum load applied, whereas the angled abutments exhibited deformation and failure at a very earlier load. And existence of microgap at the implant abutment interface was found, with greater microgap found at the implant abutment interface with angulated abutments. And these are my references. Thank you.